This video brought to you by Snake Lego guy, something I'm not as familiar with these. I think this is a Chimea, that line of Lego. Anywho, so now that we know the Pythagorean identity, or the three Pythagorean identities, along with that list of basic identities, we're going to mess with simplifying expressions. And a lot of mathematics is being able to manipulate things from one form into another form. And we often use the word simplify. And one of the problems is, what does it mean to be simplified? And of course, to someone that's not a big fan of math, nothing in mathematics looks simple, right? So simplify can mean many things. Boy, let's just do one and you'll kind of see what happens. And then maybe we'll try to come back and make up a list. So we've got some directions here. It says multiply and then simplify. So let's do the multiplication first. Notice this is a product right here. This is sine or cosine x times sine x. And then we're multiplying that times secant x plus cosecant x. So that's just a direct application of the distribution property. And we'll get cosine x times sine x times secant x plus cosine x times sine x times cosecant x. Okay, so the simplification part is, well, maybe there's a way we can use basic identities to rewrite this in a simpler form, whatever that might mean. And I think you might note that secant could be written as 1 over cosine, and cosecant could be written as 1 over sine. Well, if we note that, we could then rewrite this expression as that times this, and this times that. Don't forget the plus sign, and then that times sine x, and times cosine x. And then when you have, these are really over 1, right? So when we have the same factor in the numerator and the denominator, we can divide those away, right? And this left side, or this piece of the sum, becomes sine x. And over here, that goes away. This becomes cosine x. Now, at this point, I think I would win an argument if we were to say which of these three lines is simpler. This is the simplest one. All right, let's try another one. So here we are to factor. So this is old school stuff. We're looking at like common factors or whatever we can. And what I'm going to do here is do the substitution method. Way back, I think it was chapter 3, where we noted that if this is in quadratic form, we could rewrite it in a different thing. So I'm going to say, let's let x equal sine of t. And then if I square x, that's just going to equal sine of t parentheses squared, which is really just sine squared t. So I'm going to rewrite this expression as 4x squared plus 8x plus 4, and I'm going to factor this much more familiar expression and then plug back in what x was equal to. Now, you don't have to do this. Maybe you could note that we could just let x, or just factor it right from here. Awesome, that's great. That's what we would want you to be able to do. All right, so note there's a least common factor, or at least whatever it is, divide everything by 4, and we get x squared plus 2x plus 1. And then this looks like it's factorable, doesn't it? Like, let's see, x plus 1 times x plus 1, which we would probably write as 4 times x plus 1 squared. I think in the calculus world, this would be a preferred expression to this, particularly if we're taking the antiderivative. Now, this is not the answer we want. The answer we want is this with what we said x was, that's sine of t. So here is our final answer in factored / simplified form. So example 5 says simplify, and to me this one's pretty clear. Whenever you saw an expression that had common factors in the numerator and the denominator, you divided those out because they were equal to 1. So we'll do the same thing here. Sine squared x divided by sine x is just sine. Cosine divided by cosine squared x is just cosine in the denominator. And so this expression becomes that sine x in the numerator divided by that cosine x in the denominator. That's that old school algebra you learned. And then now we can apply our basic trig identities. If we have sine divided by cosine, that's equal to tangent x. All right, one more. Nope, two more. Sorry, three more. So here we're to add and then to simplify. Well, first we have to apply our properties of exponents. So I'm going to take this -1 over cosine squared x and just leave it alone for the time being. And I'm going to add to it, well, this is just, the squared needs to be applied to both the sine and the cosine. All right, now you recall that adding fractions, you have to have a common denominator. Oh, glory days, they already have a common denominator. So we can write this with a single denominator. And I'll write the sine squared first, just for fun. So here it is. Now, you may not know this yet. You might look at this and not see what I see, but I see this because I've done thousands of these problems. And from here on out, you're going to see this as well. That sine squared x minus 1 is suspiciously similar to sine squared x plus cosine squared x equals 1. In fact, if I solved for cosine squared x in this problem, I would get that exactly. In other words, I'm going to take the Pythagorean identity, sine squared x plus cosine squared x equals 1. I'm going to subtract sine squared x from both sides. I can do this, by the way, because I know this is a true statement, this equality. I know this is identity, so I can solve this for any one of the three terms in the equation. So noting this, that 1 minus sine squared x is the same as that, oh, wait a minute, it's not. Because here sine is negative and the 1 is positive. Well, I can fix that. Factor out a -1 from this, and we'll get negative sine squared x plus 1 all over cosine squared x. Well, this is exactly the same as that, so we can rewrite it as cosine squared x. So my numerator becomes -1 times cosine squared x. Boy, that's an awkward cosine there. There we go. And my denominator is still cosine squared x. Well, look at that. Cosine squared divided by cosine squared is 1. So this final answer is -1. Isn't that awesome? All right, two more. Two more examples of simplifying and doing some sort of arithmetic. Okay, rationalizing, you may recall that means to remove the square root from the denominator. I should mention that the way I'm showing how to do these problems is not the only correct way to solve them. This one has multiple ways. What I'm going to do first in this problem is I'm going to apply the radical to both the numerator and the denominator. So that's going to be cosine x, square root of cosine x in the numerator, square root of tangent x in the denominator. We could have turned this into sine over cosine and messed with that right off the bat, but I'm going to do that last. So to rationalize this, I'm going to multiply by 1. And I'm going to multiply by a 1 that removes the radical from the denominator. That happens to be the same thing as what's in the denominator. Because when I do square root of tangent x times the square root of tangent x, I get the square root of tangent x squared, which is just tangent x. Now in the numerator, I'm going to smash these two together into a single expression within the radical, cosine x times tangent x. Of course, I'm allowed to do that. You may recall the two properties of radicals. We could do this, and we could do this. Of course, we have to be careful with the signs of these things. A and B can't both be negative. And also B can't be 0 in this one. All right, so here's our thing. We've rationalized it, but we can mess with this stuff in the radical in the numerator. Sorry, I started eating a jelly bean. That's ridiculous of me. All right, so we could do cosine x over 1 times tangent happens to be, well, boy, do I know what that is? It's sine over cosine. Of course I know what that is. Yeah, so this would become sine x over cosine x. And you can see why I'm doing this, right? Those cosines cancel, and that means that cosine x times tangent x is really just sine x. So our numerator is the square root of sine x divided by tangent x. And now we're done. We have rationalized the denominator, and we've simplified this expression that was left in the numerator. Okay, promise. Last example of this stuff, and then we'll do a sum and difference identity. This is just kind of an interesting little thing. We're given an expression, and then we're told to rewrite it without radicals if x is equal to 4 secant theta, and we're assuming that secant theta is between 0 and pi halves. And of course, we can't include pi halves because that's undefined, and we can't include 0 because that's undefined. And then this guarantees that our x's are all positive. So the first thing we're going to do is we're going to put the 4 secant squared into the expression, and then we'll start messing with it from there. Now be careful. A common mistake I see students make when they write something like this is that they apply the squared to the secant, but they don't apply it to the 4. These are two bases, so this is an example of a times b raised to the n power, which is equal to a to the n times b to the n, which is why we have to write this as 4 squared secant squared and 4 squared secant squared. Okay, so let's do that. We still have this radical. We haven't messed with that yet. We've got 16. That's 4 squared, by the way. And then secant squared minus 16. And then the denominator, we've got 16 times secant squared. Okay, so the goal here is to somehow eliminate this radical in the numerator. Well, we have to do a little bit of work. First, let's factor out that 16. That seems to me to be a very obvious thing. That's a nice perfect square, so there's getting rid of one radical. And then we should look carefully at the secant squared minus 1. Doesn't that seem suspiciously similar to the problem with the Pythagorean theorem? Doesn't that seem really similar to this kind of expression, right? So there's a good chance that we could take one of these Pythagorean identities and rewrite them in a similar form as this. So look at the one that contains secant. Wait a minute, if I subtract 1 from both sides, I get the tangent squared equals secant squared minus 1. Let me write that. Boy, where do I want to write that? I'm going to write that right over here. So I've got 1 plus tangent squared theta equals secant squared theta. If I solve for tangent squared by subtracting 1, I get that tangent squared theta equals secant squared minus 1. Now, you may not have thought that on your own. That's how I thought when I first saw these things, but now I think that way, and you will too. So that means this entire piece is just tangent squared theta. Well, that's beautiful, right? Because I know the square root of a squared is that thing. So if you look at what's happened, the numerator has become a product of two perfect squares that we're taking a square root of, and we know how to handle that mess. It's this thing that I wrote up here. We're going to take the square root of each piece individually. In other words, the square root of 16 is 4. The square root of tangent squared is tangent. And in the denominator, we got all this mess. All right. Now the question is there anything that we can simplify with this? Well, obviously the numbers, right? So that's this. Okay, let me just rewrite that mess. So that's tangent theta over 4 secant squared theta. This might be a nice simplified answer, but maybe we don't like this secant in the denominator. So I'll do that as a little aside over here. We could write this as tangent theta over 4 times 1 over cosine theta. That's a cosine squared theta, which then would become, boy, at this point, I'm going to be popping a cosine into the numerator. So it feels like we should rewrite tangent as sine theta over cosine theta. And then I'm going to end up multiplying by the reciprocal of this because of the division. So that would end up being cosine squared theta over 1. And then let's see, one of these goes away with one of those. And so we get sine theta times cosine theta all over 4. So now we can start arguing which of these two is simpler. And I don't know, I guess it depends on what you have to do with it.